Dr. Tolles conducted his PhD research at Stanford University during most of the 1980s under the direction of Professor Helmut Krawwinkler, supported by a grant from the National Science Foundation. This research was directed towards understanding the seismic behavior of rural adobe houses and how to improve their seismic performance with simple seismic retrofit measures. The models were 1 to 5 scale models based upon prototypes from houses in Mexico with 16-inch thick earthen walls, a low-strength adobe material of approximately 150 psi, and a 6-inch earthen roof. There were lead weights attached to the tops of the walls in Model 1 to simulate the 6-inch earthen roof. During Test 6, Model 1 nearly collapsed. The peak ground acceleration of 32% of gravity and the peak displacements was just over 6 inches. Were it not for the connectivity of the long out-of-plane walls to the short transverse walls on the left side of the screen, the model wall would clearly have overturned. Model 1 was easily destroyed by the ground motions during Test 7. The peak ground acceleration was over 40% of gravity and the peak displacements were over 7 inches in the prototype domain. The rear wall nearly collapsed at the beginning of the test sequence. The front wall easily overturned during the test. And the rear wall also collapsed near the end of the test sequence, as you see here. Model 3 was originally intended to be the starting point for this research effort, but we soon realized that the anchored roof beams, as installed on this model, were a significant seismic improvement measure in and of themselves. The roof beams were anchored to each wall, which effectively coupled the front wall, that had a door and window opening, to the rear wall that was solid with no openings. The connection by the steel roof beams tied the front and rear walls together at their tops, which had a significant impact on the out-of-plane stability of these two walls. Test 6 nearly caused the collapse of Model 1, but was not nearly strong enough to cause the instability of the out-of-plane walls of Model 3. The roof beams tied the long walls together, allowing them to rock gently back and forth throughout Test 6. Test 7 easily caused the collapse of both the front and rear walls of Model 1, but the roof beams of Model 3 were still enough to stabilize the long, out-of-plane walls throughout Test 7. Although their displacements were nearly half the thickness of the walls, they still remained stable. In fact, the failure of the model was not the long out-of-plane walls, but the in-plane wall, which suffered severe shear cracking and the subsequent slippage of the cracked sections of these walls along the downward sloping crack planes, which led to failure of the end wall perpendicular to the primary motion of the shaking table. You will now watch a slow motion repetition of the collapse sequence of Model 3, showing the continued rocking of the long out-of-plane walls, while the shorter in-plane wall is destabilized by the in-plane shear cracks and slippage along these cracks, until this movement resulted in the out-of-plane failure and overturning of the end wall.